Hello, welcome back to the first course in general physics. We are still talking about thermodynamics of systems, and in this lecture we will be discussing the first law of thermodynamics, and then we will take some special cases of the first law of thermodynamics, special cases where one of the physical quantities is zero, which simplifies the shape of the form of the second law, and then we will have an easier solution for a given problem. And then we will be discussing the different types of thermodynamic processes. So we start with the first law of thermodynamics, and we continue the discussion from last lecture. We have discussed in the last lecture the thermodynamic processes and the fact that in taking a system from an initial state with specific volume, pressure, and temperature characteristic of the initial state to a final state with pressure, volume, and temperature characteristic for that state, then the work done, W, and the quantity of heat absorbed or released by the system, Q, depend on the path which we take in transforming the state of the system from the initial state to the final state. So W, the work, depends on the path. How do we move from the initial state to the final state? And also Q, the heat absorbed by the system or released by the system, will also depend on how do we move from the initial state to the final state. However, it was found experimentally that there is a quantity which is the difference between these two quantities, the difference between heat absorbed and the work done by the system. The difference is always constant, regardless of the path taken by the system as it changes its state from the initial state to the final state. So Q minus W is always a constant. That is an experimental fact. Other quantities or combinations of Q and W, such as Q plus W or Q minus 2W, or whatever other combination, is path dependent, except this particular combination, Q minus W. That leads to the conclusion that this quantity, which is Q minus W, is a quantity that is correlated with an intrinsic property of the system. And this intrinsic property of the system is the internal energy, which depends only on the state of the system. It is a state functional. So since Q minus W is state dependent, this quantity is the internal energy of the system, which is also state dependent. If you know what is the temperature, what is the volume, and what is the pressure of the system, the state parameters of the system, then the internal energy is defined completely. Thus, we arrive at the first law of thermodynamics, which is a statement of this fact, which says that the difference in internal energy of a system as it changes state from an initial state to a final state is equal to the heat absorbed in this process, Q, minus the work done by the system, W. And we have to take into consideration the signs here. Q is positive if the system absorbs heat, and Q is negative if the system releases heat to the environment or loses heat, Q, to the environment. Then Q is negative. And again, the definition of the sign, or the sign convention for the work, is that if the system does work, then the sign of the work is positive, and if work is done on the system by the environment, then the sign of the work is negative. So thus we obtain a relation for the change in the internal energy in terms of the heat absorbed and the work done, or vice versa, or alternatively, in another form, if the system changes its state by an infinitesimal amount, meaning if it initially has a pressure Pi, volume Vi, temperature Ti, and each one of these parameters changed infinitesimally by dt, by dV, by dP, each quantity changes infinitesimally, then the total change in the internal energy, which is dE internal, is equal to the infinitesimal heat absorbed during that infinitesimal change of state, dQ, minus the infinitesimal work done during that change, dW. D goes for a small amount of change, indicating that the state changes only infinitesimally. We notice in this alternative form of the first law that the D with the energy, the internal energy, is a regular D, a regular differential. However, the D which is associated with heat absorbed and work done is a different kind of D. It is a crossed D, and this is to indicate that dQ and dW are inexact differentials. This cross with the D on the D of the dQ and the cross D cross of W indicates that those dW and dQ are not exact differentials, because Q and W are not state dependent, are not state functionals in a way. They are just the amount of heat transferred into the system or from the system, and the work done by the system or on the system. They are not functional state functionals. So we write them in this form, but as far as we are concerned, we consider them an infinitesimal amount of heat absorbed and work done. So an the first law of thermodynamics is thus an extension of the principle of energy conservation that we have been discussing in the context of discussing the dynamics of systems. In the context of the discussion of dynamics of systems, we have taken into consideration systems that are closed and isolated, where no forces are acting on the system, and isolated systems where no heat is added to the systems, for example. In this case of the first law of thermodynamics, we take the case where the system is open, the system is not closed. The system can interact with the environment and lose heat or absorb heat from the environment. Also, the system can do work on the environment, or work can be done on it by the environment. So in that case, the system in the first law of thermodynamics is not a closed system. But we have taken the case where the total kinetic energy of the system is not changing, and the average potential energy of the system is not changing. So we are taking the case where only heat and work are involved in changing the state of the system. So in that sense, this conservation law is an extension to the conservation law of energy, but applied to a non-closed system, and also under certain conditions where, for example, the potential energy of the system is the average potential energy of the system is fixed. And now we discuss special cases of the first law of thermodynamics. We discuss cases where the quantity Q, heat absorbed, is 0, or the quantity W is 0, or the quantity delta E, the internal energy, is 0, or all of them are zeros, or Q and W are zeros. We discuss such cases, special cases, where one or more of the quantities in the first law of thermodynamics is 0, which makes the shape or the form of the first law a simple form to deal with. So the special cases in which one of the quantities is 0 are, one of them is the adiabatic process. The adiabatic process is a process in which the heat absorbed by the system, Q, is equal to 0. This process will be discussed later a little bit more in more details. And since Q is equal to 0, then the first law takes a particularly simple form, which is delta E internal is equal to minus W, the work done by the system. So the work, in this case, the work done by the system is represented as a change in the internal energy. And if the work done, if the system does work during an adiabatic process, then the energy of the system, the internal energy of the system, drops down, because delta E is equal to minus the work done. Take into consideration the sign. So the next special case is the case of a constant volume process. a process taken at constant volume, or the so-called isochoric process. This process, we take the system from an initial state to a final state, keeping the volume of the system constant. And since the volume is constant, we recall the definition of work done by the system. The work done by the system is simply the integral of the pressure of the system times dV, the change in the volume. And we integrate over the change in the volume of the system. Since the volume doesn't change, it's an isochoric process, constant volume process, that is, then we conclude that the work done is zero in this special case. And since the work done is zero, then the internal energy of the system changes as heat is absorbed or released by the system. So delta E is equal to Q. And the sign of Q, whether the system absorbs heat or transfers heat to the environment, decides whether the internal energy of the system increases or decreases. The third special case is the cyclical process. The cyclical process is a process where the system starts from an initial state taken to a final state, some other state, and then back to the initial state. So the definition of the cyclical process is that the system is restored to its initial state, and since the internal energy is a state functional, it depends on the state. So when the system goes back to its initial state, that means the change in its internal energy is zero. So delta E internal, in this case, in the cyclical process, is zero. And in this case, the first law of thermodynamics tells us that the heat absorbed by the system must equal to the work done by the system. So in a cyclical process, the system absorbs heat, attains heat, and does work. An example on this case of a system where the system absorbs heat and does work is represented in this figure. This figure shows a cyclical process where the system starts from initial state I, taken to a final state F, each one of them having the parameters of the state, pressure, volume, and temperature, and then restored back to the initial state. The work done by the system during this cyclic process is this area enclosed in this loop, inside this loop. And this area is positive. It's greater than zero. The net work done is positive because the area under the upper curve from going from initial to final, which is the work done during this process, is larger than the process taking the system from F to I. The work done in taking the process from F to I is smaller than the work done by the first process from I to F by the amount which is the area of the loop. Now, this area of the loop, according to the first law of thermodynamics, is equal to the heat absorbed by the system. So we conclude in this case that during this process, the system absorbs heat, Q, and does work, and those two quantities are equal. An example on this is the human body. That's an example on a system which goes through a cyclical process. The body of the human being goes through such a process where the body obtains heat from the metabolism of food intake. So the human being eats food and metabolizes this food, and thus obtains the heat, Q, the energy, and the human being during activities such as breathing, which is doing work, walking, which is also doing work, and other activities like reading or going from one place to another to lift objects or whatever. All of these activities involve doing work, and the work done by the system, if the human body starts, let's say, from an initial point and goes back to the same point, to the same state, then we say the human body went through a cycle. And this figure illustrates this cycle. Let's look at the processes that the human body goes through. So we have, for example, we start with the sleeping and assume that the human body, the human being, sleeps for 8 hours. The work done by the human being during sleeping, which is due to breathing and slight motion during the sleeping time, is estimated to be 2 million joules, 2 times 10 to the 6 joules. And after sleeping, the person wakes up and has breakfast usually, and the heat intake or the metabolism of food would provide the human body with heat Q that is equal to 5 times 10 to the 6 joules, 5 million joules. And assuming that the process of eating the breakfast takes 1 hour, the work done during this 1 hour by the human body in chewing the food, in breathing, in doing things like that, in moving, the work done is estimated to be 0.7 million joule. And then after breakfast, the person goes to work. The morning work, which is estimated to be taking 4 hours, during these 4 hours, the work done is estimated to be 4.3 million joules. And then we come to the lunch hour. Suppose that lunch takes 1 hour. We have a heat intake, a heat absorbed during lunch of about, again, 5 million joule. That's Q absorbed during lunch. And the work done during the 1 hour lunch time is again also estimated to be 0.7 million joule during this hour of lunch. And then after that, we come to the afternoon work, which is also estimated to be a 4-hour work. During this period of time, the work done by the human being is estimated also to be 4.3 times 10 to the 6 joules, or 4.3 million joules. The dinner after the afternoon work, after the end of the day, the dinner is a process which provides the human being, the human body, with a heat of 6.5 million joules. And assuming that the dinner time also takes 1 hour, the work done is 0.7 again, million joules. And after that, suppose that the human being goes through exercise for 1 hour, spending 2.1 million joules. And finally, the evening time, during the evening time of watching TV or reading or whatever, studying, suppose that this time with the breathing and regular motion of the human body spends 1.7 million joule. So suppose that these are the activities and the heat absorbed through metabolism of food during the daytime. The net result of these processes is that the heat obtained by the metabolism of food is simply 16.5 million joules, and the work done by the several activities of the human being is also 16.5 million joules. The increase in the internal energy is thus Q minus W is 0. And that's assuming that the human being is a healthy person who spends the energy that he or she takes during the eating processes. Of course, if the work done is less than the heat or the energy absorbed through metabolism of food, or vice versa, if the work done is more than the energy obtained through the metabolism of food, then the story is different, and there is a net change in the internal energy. But assuming that there is no such change, assuming that the process is really cyclical process, then this is an example of this process. The other example of the special cases of first law of thermodynamics is the free expansion of gases. If we have a gas enclosed in a container and it expands freely, and if the process is adiabatic, which means that the system is insulated, there is no heat added or absorbed or transferred, and the system does not do any work. So in this case, Q is equal to 0 and W is equal to 0. And from the first law of thermodynamics, then delta E internal is equal to 0. So in the case of free expansion, such as in this figure, where initially we have the gas confined to the to one side of the container by a stopcock, and the other half of the container is vacuum. If at a certain point we release the stopcock or we open it, then the gas rushes to the second empty half, expanding. But during this expansion process, it does not do any work because it does not do anything against anything else. Of course, when it bangs the walls of the second container, which was initially at vacuum, it does not do any work because it bangs the walls do not move. So there is no work done against anything, although the gas expands. At the same time, because the system, as the figure shows, because the system is well insulated, then no heat could enter the system or no heat could leave the system. So this is the case of the free expansion of gas. In the case of the free expansion of gas, we will encounter a problem of finding some quantities for such an expansion, some thermodynamic quantities. We will face a problem because in this case of expansion, we do not have a PV diagram for this process. We cannot draw the process on a PV curve. We do not know what is the relation between the pressure and the volume at any moment during the expansion of the gas, during the free expansion of the gas. We only know the initial state. We know the pressure, the volume, and the temperature of the initial state. We also know the volume, pressure, and temperature of the final state, where we can measure them. But we do not know these quantities at any transient period during these during the transition from the initial state to the final state. So this will introduce a problem in finding the various thermodynamic quantities, but we will learn how to go about around this problem. And now I am at the point where we are ready to discuss the types of processes. We have talked about thermodynamic processes, and we have shown the diagrams on a PV curve, or we have spoken about the free expansion, for example, where we cannot draw a PV curve for the process. What are the types of processes? Now, in this at this point, I would like to consider specific types of processes which can be handled in a controlled manner and which allows us thus to track the transition from one state of the system to another state and evaluate the different thermodynamic quantities and understand the thermodynamic properties of our system. So we move to discuss cases which can be done experimentally in a controlled manner, like, for example, a process under constant volume, for example, a process under constant pressure, and so on, under constant temperature, whatever. We can control these processes. This is now what I am discussing at this moment. And one of the processes which can be done in a controlled manner is the adiabatic process that we just discussed a moment ago. And we said that in this process, Q is equal to 0. How does this happen? How does a process happen where Q is equal to 0, for example? We have shown an example in the case of the free expansion of gas, where we insulate the system. Actually, we have another way of having a process where the heat absorbed by the system is 0, or the process is adiabatic. If the process occurs so fast, then the heat, the amount of heat Q is equal to 0 during such a process. Or if the system is very well insulated. What are examples of a system that of a process that is occurring very fast, that it does not allow any time for heat transfer? Sound waves is an example. We know that sound waves consist of compressions and expansions of the portions of the air, and that's how the sound is delivered from one point from the source to another point, the detector. Since we have changes in the states of the system, which is the air in between, during the compressions and the expansions of the different portions of the air, which causes the transport of the sound wave from one point to another in space. The question is, since we are changing the state of the system at different locations and transport of the sound occurs, why don't we have energy transport? Why don't we move Q, heat, from one point to another, just like we move the sound from one point to another in the same process, because it's exactly the same process? The answer is that because these compressions and expansions of the air, they occur so fast that there is no time for heat absorbed or released. So it is an adiabatic process. Sound waves are example of the adiabatic process. In this case, Q is equal to 0. In this case, the first law tells us that the internal energy, the change in internal energy during the process is equal to minus W, the work done by the gas on the environment. And how do we control this process? As we mentioned, we control this process in two ways. One way is if the process is done so fast, like in the case of the sound waves, for example. In another way, if we cannot do the process very fast, then we have another way of controlling it, which is by insulating the system very well up to the point that it does not lose any heat. And this is an example of a system that is very well insulated, and we have gas enclosed in a cylinder, and the cylinder is covered with a piston that moves without friction, and on top of the piston there is a container that has lead shot in it to make a weight which decides the pressure of the gas. And now if we start removing lead shot pieces piece by piece, then the gas expands. The piston goes up because the pressure on the piston is decreasing as we remove weights from the top of the piston. As the pressure decreases, the piston rises and the gas pushes the piston upward, doing some work. And the work done in this case is positive because the gas does positive work on the environment in lifting the lead shot container. In this case, the energy of the system drops down. Delta E is equal to minus W, and W is positive, so the energy of the system drops down. So during an adiabatic expansion of a gas, the internal energy goes down. And vice versa, if we start adding lead shot or weights on top of the piston, then the piston goes down and the system is compressed, the volume decreases, there is no heat, the work done is negative because the volume decreases. Since the work is negative, then from the first law, the delta energy, internal energy, is equal to minus the work, which is a positive quantity since W itself is negative, and that means in the adiabatic compression, the energy of the system increases. This is how we control this process, which is the adiabatic process. And in the adiabatic process, the internal combustion engine has processes where we have an adiabatic expansion and adiabatic compression of the gas in the cylinders in the internal combustion engines, and these processes are adiabatic during the compression and the expansion of the gas in the cylinder, due to the fact that these processes occur so fast up to the point that we have an adiabatic process. And now we consider the isochoric process, which we have considered previously, which is the process at constant volume. A constant volume process is characterized by zero work done by the system, and thus the added heat to the system raises the internal temperature of the system while its volume stays constant. So this is a relation between only the internal energy and the heat, and thus delta E internal from the first law of thermodynamics is equal to Q. And this relation is a relation between the internal energy and heat absorbed. An example on this process is the heat added to a gas that is contained in a constant volume container. In this case, when we heat up the system, heat is added and the internal energy rises while the volume of the system remains constant. At this point, I would like to end this lecture, and I thank you for your attention.